Good morning, everybody. We are going to have such a good time, I'll tell you that.
5, 4, 3, 2, 1. Hold on tight.
First stage propulsion nominal.
Well, good morning, everybody. I'll start the story that I said I'd do today, but I won't do it all in one go. I'll break it up into chunks. I know there are people on the bus who know quite a lot of physics, and there's people on the bus who don't know a lot of physics, so I'm going to try and start at a fairly basic level. All of it relating to the experiments that were going on at Homestake Mine, and also at Fermilab too. There's a number of bits of background that I'm going to give you first to try and set it in context. The first bit of background is about our quest to understand the way everything around us is made up. When we look around us, we see a universe that's made of matter. And from the earliest times, from the Greek Democritus, people have wondered how that matter was composed. And Democritus came up with the idea of everything being made up of individual, small, indivisible particles called atoms. And for most of recorded history, that idea was followed up, and most of recorded history was resulted in people looking for different kinds of atoms. And we ended up with 92 naturally occurring elements, from hydrogen, the simplest atom, to uranium, the most complex. It wasn't until the very end of the 19th century and the beginning of the 20th century that physicists began to probe whether atoms really were indivisible. And of course they're not, because they eventually found out that atoms can be divided at the simplest level into a central nucleus, around which are a number of orbits or shells containing other particles. Now, the nucleus of an atom generally will contain protons and neutrons, and the orbital shells around contain electrons. Neutrons have no electric charge, protons have a positive charge, electrons have an equal and opposite negative charge. So in a neutral atom, you'll have a number of neutrons and protons in the nucleus, and the number of electrons in the shells around will exactly equal the number of protons. So the atom is electrically neutral. And that idea prevailed until the middle of the 20th century, when people realized that even those particles, the protons, neutrons and electrons, were themselves not indivisible. That they were themselves made up of even more fundamental particles. And as we've gone through the last 50, 60 years, we've realized that there is what I'm going to call colloquially a particle zoo. A whole large number of different sorts of particles that make up the universe in which we live. And one of the pieces of work going on at Fermilab and Homestake Mine is to try and understand those fundamental particles that make up everything at the very, very basic level. The second bit of background is to go right back to the Big Bang, 13,800 million years ago. The universe, we believed, was formed in this fireball of energy from which all matter, space, time began. Now, it's pretty fundamental in the early history of the universe to recall Einstein's famous equation E equals mc squared. Now, it means that energy and mass are equivalent. you can have a particle of a certain mass m being turned into an amount of energy equivalent to that mass times the square of the speed of light. But it also goes the other way. You can have an amount of energy which you can divide by the square of the speed of light and produce out of that energy a particle of mass m. In the early universe, matter and energy were being swapped all the time. As the temperature of the universe declined after the Big Bang itself, obviously the universe was expanding and the energy was becoming more distributed. But what was happening in that period, the so-called, what I call particle soup era, was that particles were forming from energy and they were annihilating with each other to produce energy again. And what is really, really fundamental is that according to our ideas of the universe, matter and antimatter were formed in exactly equal quantities. In other words, in all of these mass-energy interchanges in the post-fireball era of the Big Bang, in the particle soup era, equal numbers of particles and their antiparticles were being formed. The problem is, when we look around us here, we see a universe made of matter. When matter and antimatter meet, they annihilate, producing energy in the form of gamma rays. It appears that for some reason in the early universe, the amount of matter was greater than the amount of antimatter by 1 part in 8 billion. And this is proven also when we look around us and find that there are 1 billion times as many gamma ray photons or photons of energy as there are particles of matter. So for some reason, matter and antimatter were not produced in exactly equal amounts. The amount of matter was slightly greater than the amount of antimatter by 1 part in 8 billion, and we do not know why. So the second type of experiment going on, Fermilab and Homestake Mine, is to try and unravel the mystery of why is it that matter outweighed antimatter by 1 part in 1 billion in the early universe. And all the bits annihilated, leaving that 1 billionth part to make up the matter of the universe that we see today.